Ever wondered how your computer understands the language you speak? Imagine a world where computers and humans speak the same lingo. A realm where the gap between human languages and machine code is bridged. Enter the world of formal languages and automata theory, where this seemingly science fiction idea is a reality. At the heart of this world lies a computational model known as a Pushdown Automaton, or PDA. This model is a step ahead of its predecessor, the finite automaton, and it possesses an additional tool, a stack, a last-in first-out data structure. This stack is the secret weapon that enables the PDA to handle languages more expressive than the regular ones, the so-called context-free languages. Now, why does this matter? Why do we need machines to understand human languages? The answer is simple. It enables us to interact with machines more naturally and efficiently. Imagine asking your computer to find all the photos from your last summer vacation instead of manually searching through folders. Or asking your smart home device to adjust the room temperature to your liking without pressing any buttons. That's the power of effective language understanding. A PDA is more than just a theoretical concept. It's a crucial component in various practical applications, from compiler design to natural language processing, and even parsing structured data formats. The PDA's mechanism of transitioning from one state to another based on the current state, the input symbol and the symbol on top of the stack, provides a formal model for parsing and recognizing context-free languages. So, the next time you interact with your computer or any digital device, remember there's a PDA working behind the scenes, understanding your language, making your interactions seamless and intuitive. The world of Pushdown Automata is a fascinating one, full of mysteries and wonders. It's a world where computers understand us, where our languages become their languages. Intriguing, isn't it? Let's delve deeper into this fascinating world of Pushdown Automata. Now imagine a machine. It has a few components, each playing a crucial role. This machine, called a Pushdown Automaton, or PDA, is a theoretical model used to understand complex computational processes. Let's break down its 6 main components. First, we have the states. Picture them as rooms in a sprawling mansion. The PDA can only be in one room or state at a time, but it has the freedom to move from one to another. Next, we have the alphabet, which is a set of symbols the PDA reads from an input string. Think of these as the messages or instructions the PDA receives. Then comes the stack. This is like a magical box that can hold an infinite number of items. It has a special rule though. The last item you put in is the first one you take out. This stack lets the PDA store symbols for later use. Now, the transition function is the rulebook of our PDA. It spells out how our PDA should move between states based on the current state, the input symbol being read, and the symbol at the top of the stack. It's like a guidebook that tells the PDA where to go and what to do next. The initial state is the starting point of our PDA. Like the front door of the mansion, this is where the journey of computation begins. Finally, we have the accepting states. These are special rooms in our mansion. If the PDA ends up in one of these rooms after reading all the symbols from the input string, it means the input string is accepted, or in other words, understood by the PDA. Together, these components give the PDA its power. They allow it to recognize patterns and structures in data, making sense of complex languages and inputs. Each component, working in harmony, brings the PDA to life. So, how does this machine, the PDA, operate? Well, let's break down the process, shall we? Imagine the PDA as a well-designed engine. It starts its operation in what we call the initial state. Picture this as the engine's idle mode. It's ready and waiting for action, but nothing's happening just yet. The stack, our special last-in first-out storage, is empty at this point. Now the engine starts to rev. The PDA begins to read input symbols from the input string, one symbol at a time. Think of these symbols as prompts or commands that tell the engine what to do next. As the PDA reads each symbol, it's also considering the current state it's in and the symbol at the top of the stack. Like a skilled mechanic, it takes in all these factors, then performs a transition. This transition is a movement to a new state, a shift in the engine's gears. But that's not all. As the PDA transitions, it also updates the stack. It might push a new symbol onto the stack, or pop the top symbol off. Sometimes it might not do anything to the stack at all. This is like our engine adjusting its components for optimal performance. Once the PDA has made its transition and updated the stack, it moves on to the next input symbol. It's as if the engine is maintaining momentum, driving forward to the next command. It continues this process, reading symbols, transitioning states, and updating the stack until it has processed all the input symbols. Now here's the final test. Does the PDA accept or reject the input string? This is like asking, did the engine successfully complete its journey? If the PDA ends up in an accepting state with an empty stack after processing all the symbols, then yes, it accepts the input string. It's like saying, the journey was a success. If not, the PDA rejects the input string, and it's back to the drawing board. Just like a well-oiled machine, the PDA smoothly processes the language we feed it. But where does a PDA find its application in our day-to-day life? You may wonder. Well, the practicality of pushdown automata, or PDAs, isn't confined to the realm of theoretical computer science. They are very much a part of the real-world applications that we interact with every day. Let's start with compiler design, a crucial area where PDAs really shine. You see, compilers are programs that translate source code written by humans into machine code that computers can understand. And how does this translation happen? It's through parsing, a process that involves checking whether the source code follows the rules of the language it's written in. Here, PDAs come into play, providing a formal model for parsing and recognizing context-free languages, which are often used in programming. Next, let's move on to natural language processing, or NLP. This is a field of artificial intelligence that focuses on the interaction between humans and computers using natural language. This is where your voice assistants like Siri or Alexa come in. They use NLP to understand and respond to your voice commands. And guess what? PDAs are an integral part of the underlying models that make this possible. They help in parsing the sentences, understanding the syntax, and generating responses, all in real time. Lastly, let's talk about parsing structured data formats. When we interact with a website, for instance, the data that flows between our browser and the server is often in a structured format like JSON or XML. These formats need to be parsed to extract useful information. PDAs help in recognizing these formats and thus play a significant role in making our web interactions smooth and efficient. So, the next time you code, interact with a voice assistant, or even browse a website, remember that there's a PDA working behind the scenes, ensuring everything runs smoothly. From the apps we use to the websites we browse, PDAs are silently working in the background, making our digital interactions seamless. So, we've unraveled the mystery of the Pushdown Automata. Pushdown Automata, or PDA, is a unique computational model that extends the capabilities of finite automata, with the addition of a stack as an extra storage mechanism. This last-in, first-out data structure allows the PDA to temporarily store symbols from the input string and symbols generated during computation. The key components of a PDA are the states, the input alphabet, the stack, the transition function, the initial state, and the accepting states. Just like a well-oiled machine, these components work in harmony, allowing the PDA to operate efficiently and effectively. The PDA starts its journey from an initial state with an empty stack. As it reads input symbols from the input string one by one, it transitions from one state to another. This transition is based not only on the current state and the input symbol being read, but also on the symbol at the top of the stack. The PDA then updates the stack contents and continues to the next input symbol. If it reaches an accepting state with an empty stack after processing all input symbols, it accepts the string as part of its language. If not, it rejects the input string. Pushdown automata play a pivotal role in recognizing context-free languages, a class of formal languages that are more expressive than regular languages. Their applications are wide and varied, extending from compiler design to natural language processing and parsing structured data formats. Indeed, the concept of PDAs is fundamental to the theory of formal languages and automata theory. In the vast and complex world of computer science and technology, Pushdown automata stand as a testament to the power of abstraction and the beauty of computational models. They are the unsung heroes, tirelessly working behind the scenes to bridge the language gap between humans and machines. Next time you use a digital device, remember there's a PDA working tirelessly to bridge the language gap between you and the machine. Until next time, keep exploring.